find that information. Okay? So first we look at the sun up here, and you say, well, this is where we get what? All our radiation up there. We look at this thing, it's got all kinds of things. This is just a picture. Usually sun is composed basically of what? Some of the elements that hydrogen, and you have what? Helium, and then you have some sort of what? Different kinds of what? Of heavy elements up there, and then you have, it's gas, and it swirls all around it up here, and you have some sort of a gravity up here, magnetic fields, heat energy, all kinds of things. Gravity creates all kinds of pressure up there, and that pressure up here, at the center of it, okay, and does what? A nuclear fusion, some sort of a reaction up here, okay? And then what happens when the reaction takes place, what happens? You release a tremendous amount of energy, okay, and that thing, the energy from the center of the sun, it's going to go up, okay, radiates all the way to the outer, okay. Then that energy up here goes from the center of the sun, goes all the way to the out, and then it escapes into the space up here, goes into two forms of light and heat. We get heat, and we get actually light up here. So actually, if we define what a radiation is, it's probably the energy that expands outwards from a source in the forms of wave and the particles. Of course, some of us will say, well, that was a wave, what is a particle? Okay, what is a wave and what is a particle? And the easiest way that I can explain what a wave is, it's just a disturbance, something happening up here. Okay, that's what a wave. And now when you look at the sea up here, you see the water moving up there, and we say, gee, that's a wave. If we look at, for example, in mechanical motion, we can describe it in a wave motion. So everything, any kind of disturbance can be explained in a form of a wave. Now, what is a particle? Particle in general up there, what's a particle up there? Well, in the old times, the ancient people came around and they said, look, the smallest physical thing that we can grasp is called what? An atom, okay, right? An atom. So any kind of a matter up here that we have is composed of atoms, but then we find out that if we can break those things up here, we can have what? Different kinds of particles up there. And the basic forms of elementary particles that we found up there that we name as protons, neutrons, electrons. And we found out that they have, if you physically have to really explain it to your grandmother, something is something that has weight, and it has what? Actually, I can weight, it has a spin, and sometimes it has what? A charge, right? So that's the easiest way that we can see. So we can have these things now, that this energy that expands up there in the forms of photons, electrons, protons, whatever the hell they are, that they have some mass, and because they have some mass up there, they can create a certain amount of energy. All right, that's physics 101. I explained it the best way that I could, up here, so hopefully we can understand it. So when you take a little picture of there, which is actually a false color image, it shows what the sun is in the looks like it. Okay, now we'll define a little bit some of the definitions. There's something that's called an astronomical unit. Now, obviously, the sun is actually from a certain distance from the Earth. So therefore, when this energy from the sun, it's got to reach the Earth, it's got to travel a certain amount of distance. Okay. Now, that energy is tremendous. It's really, really very powerful up here. So now, in order to scientists, when they have to define very, very long distances, they said, well, let's look at it. Okay. So you have, for example, the distance between the Earth and the sun, the average, because we know it changes a little bit. It's about 93 million what? Million miles. And it's usually, we call that an astronomical unit. Who cares? And it's usually used to measure distances in our solar system. Okay. It's long distance. However, we find out that those particles up there, or the light that travels extremely fast, 186,000 miles per second. So we're very, very far, and it takes about 8 minutes for radiation to reach the Earth's surface. So from the sun, the energy to reach the Earth, it takes about 8 minutes. So what? Okay, we have tremendous. So at any point in time, we find out that the Earth, it's receiving what? A lot of what? gigawatts of power from the sun. A lot of that energy up to here, it's been what? It's been absorbed and reflected. However, there's still enough to reach the Earth. So if we can capture it, it becomes very, very useful. A lot of that information is in your book. So now you get some idea what are we standing at, okay? So we look at it with a nice picture up here. We say, gee, here's we have the sun up here, and it's very, very far away from the Earth, and it takes about 8.5 minutes to reach. Okay. Now, why you say this is important? Well, we'll see. Okay. Now, the intensity now of that solar energy, solar power, we call this solar irradiance. So mathematicians have to really define it in a way that we can understand it. So they say, look, we call this solar irradiance, and we're going to express it, okay, in terms that we as electricians can understand. So we will call it the amount of watts that we would get per square meter. So how many of that intensity, if I have a square meter of an area, and I would get this intensity of the sun up here, how many watts I can capture per 1 square meter. So usually, and I will define this as we call it the solar irradiance, okay? And we find out that it's measured again with respect to a certain area that we're going to put up here, okay? Since it's measured at any point in time, the value, it's instantaneous. But what do we mean by that? Anything instantaneous means what? It can change for every moment in time. It's very similar that we have the speed of an object. So at any instant in time, there's a certain amount of what? Of power that I can capture in a certain amount of space. So if I look a picture at it, and I have a certain amount of plate, if this is 1 square meter, then I can, the intensity would be what? Measure how many watts per square meter I can capture in this particular area, okay? That's why when we define solar irradiance, we said this is the amount of power, watts, because that's what per unit area. Now, of course, from watts we can convert to all the types of units, energy units that we need, okay? But if the value, it's instantaneous. See, that's why it's when we calculate a lot of the calculations that we do, and we do the analysis of how many watts we get, a lot of times we get average numbers because we can't really do it instantaneously. Some of you guys now that you can actually install solar systems in rooftops and everything, you have up there a meter up there that actually daily measure the amount and actually store the amount of energy that you can get from the sun per day and so forth. A means of being able to justify to the customer of how many of those watts you got every day from the sun. So this way you can justify your system performance. Okay, that should be pretty clear. Okay. Now it varies as the sun goes through its normal cycles, but not by much. One of the things that is important in solar irradiance is the amount of sun that you get, the power per distance as you increase in the distance. So now there's something, this physical law that says, that they call it the inverse square law, that says, look, if we have a physical subject in here and I have the sun here, it takes a certain amount of sun. If I move this a certain other distance, it's the distance variation, it deals with something we call the inverse square law, which means it's about double the amount. So if we look at it's the amount of radiation that I would get at twice the distance from the Earth, it would be just what? 1/4 of it, or 1/4 of that amount, okay? So if I move the object 3 times, then it would be 1/9. So every time that I increase the distance from the sun, it's not that it's not a linearly proportional up there, but I would get a lot less radiation. So the farther I go, the less radiation that I would get, okay? Now, this is not really as important for us in the atmosphere. It's more important when we sell satellites with